Welcome to today's lesson. We're still talking about conic sections, and in today's lesson, we're going to focus on the ellipse. So recall that an ellipse is formed with the intersection of a plane and a double right cone. And the plane is not going to be parallel to the base. That forms a circle. It's not going to be perpendicular to the base. It's not going to be parallel to the slant. So any one of those angles in between will form an ellipse. And I've got a two-dimensional shape on the right side of your screen that is an ellipse, or an example of an ellipse. And the formal definition of an ellipse is the set of all points so that the sum of the distances between two fixed points, foci, is constant. So what does that mean? That means that if I take an ellipse, I have two fixed points for you here. This is just an example. Those are shown as those are orange dots. And I've got a point on the ellipse. We'll call that point B. Now the distance from one focus to that point, we'll call that D1. The distance from the other focus, that's that other orange dot, to the point on the ellipse, we'll call that D2. When I add those two distances up, I get what's called the constant sum. What that means is that if I take another point, we'll call this point C, and I do the same math, I take the distances and I add them, I'll get the same number. It's constant. That's why we call that the constant sum. And it's true for any point on the ellipse. Now let's talk about the parts of an ellipse, because this is where the vocabulary comes into play, and this is kind of what trips students up. So the parts of an ellipse. I've got an ellipse right here, and we'll draw two perpendicular lines connecting the long side of the the end points on the long side of the ellipse to the end points on the short side of the ellipse. And we've got the center right there where those two lines intersect. That center, we'll call that HK. Okay, and you've seen this quite a bit in your math career, so we'll call that the center. Now we've got the foci. Right? That's the plural form of focus. So we have focuses or foci. And the distance from the center to the focus is going to be C, which means the distance from the center to the other focus is also C. So the foci are the same distance from the center. Okay, they're equidistant from the center, which means, well, let's put a little ordered pair here. The one on the right, we'll call that C0, because in this case, we're moving right to get to that focus. And the focus on the left, we'll call that negative C0. We're moving left. So now let's put two endpoints on that long axis, that long line. Each one of those is a vertex. Those are the endpoints on the long axis. The distance, and the plural form of this is vertices, the distance from the center to the vertex is A. The distance from the center to the other vertex is also A. Now let's put some endpoints on our short axis, that vertical axis right there. Those are the endpoints on that short axis. Each one of those is known as a covertex. The plural form of this would be covertices. Now the distance from the center to that covertex is B, and the distance from the center to the other covertex is also B. So here's really our key things that we've got to remember, and you're going to have to reference your reference sheet, your notes, as you do like for the next several days. The distance from the center to the focus is C. From the center to the vertex is A, and from the center to the covertex is B. So now I like to write these ordered pairs here, 0, negative B. Those really aren't necessary when you're labeling, but it's just kind of nice when, okay, I'm going up, that's 0, B. I'm going down, that's 0, negative B. Okay. Now let's talk about this long axis. That long axis is called the major axis, and the length of that is 2 times A. Obviously, if the distance from the center to the vertex is A, and I've got 2 of those, then the distance all the way across from vertex to vertex is 2A. So now I've got the other axis that I'm highlighting in blue here. That is called your minor axis. And the length of that is 2b because the distance from the center to the co-vertex is b, and I've got 2 of those to show the length of the entire minor axis. So that's 2b. And now let's move on to some equations of ellipses. All right. When we're graphing ellipses and the major axis is horizontal, which is what we just talked about in the previous slide, when the major axis is horizontal, we're going to use this equation right here. Okay, and that major axis is horizontal, so it's going to look like this on your graph. So what do I notice here? I notice that I have in my numerators, okay, I have 2 fractions, but in my numerators, it kind of looks like the equation of a circle. And at this point, if you watch the previous video, I talked about circles, equations of circles. But with ellipses, I've got 2 rationals. I've got 2 fractions and I'm adding them. They're both positive. Okay, so I'm adding them. And then the other thing that I want you to notice right now is that it's set equal to 1. And this is the standard form, the standard equation of an ellipse. Now, what if I have a major axis that's vertical? That's going to look like that when I graph it on the coordinate plane. It seems very similar, but what is the difference? The difference is the a squared and the b squared have switched places. Okay, so that's really what's going to let you know how to graph an ellipse on a coordinate plane. The a value is always bigger. Okay, so when you're looking at an equation, whichever has the bigger number in the denominator, that will let you know if your major axis is horizontal or your major axis is vertical. And these, we labeled the distances from the center point to the vertex, the co-vertex, and the focus as A, B, and C. And these values are related using this equation. C squared equals A squared minus B squared. It's obviously very similar to the Pythagorean theorem. So I've heard it called, it's like the Pythagorean theorem, but it's obviously not. So C squared equals A squared minus B squared, not A squared plus B squared. So we'll use this equation when we're needing to find out some different information so that we can either write an equation for the ellipse or we can graph the ellipse, whatever. So let's move on to graphing ellipses. Go to number 1. Let's graph some ellipses. The directions say to identify the values of A, B, and C for each ellipse, then graph the ellipse on the coordinate plane. The only values I need when I'm graphing an ellipse are the values of A and B. C is here to help me find the value of A or the value of B if I'm not given that in the information. So let's look at this. I have a really basic ellipse here. X squared over 81 plus y squared over 25 equals 1. So let's first talk about what the center is for this particular ellipse. And the center, because we don't have any x minus h, x minus k, our center is going to be at 0, 0. So let's go ahead and write that down, and then let's graph it. It's at 0, 0. And now let's identify the values of A, B, and C. So one of the first things that I like to do whenever I'm graphing an ellipse is identify, is this going to be a horizontal or vertical ellipse? So then I look at my A squared and B squared values and I see what is it under? What's the largest value under? The largest value here is under the X, which means I know that my ellipse is going to be horizontal, right? If A squared is always bigger, it's going to look like this. So let's identify the value for A by taking the square root of 81, which is 9. That's the value for A. I'm going to switch colors here so you can see that the value for B is going to be the square root of 25, which is 5. And I know that because if B squared equals 25, then B equals 5, right? That's how I'm getting that. Okay, so now let's graph these 2 parts. So if the value of A is 9, that means from my center, I'm going to go out 9 units out from the side, those are the vertices, all right? Those are the endpoints of my ellipse. And now, if I'm going to graph the B values, this is the distance from the center to the co-vertex, which is 1, 2, 3, 4, 5 units up, and 1, 2, 3, 4, 5 units down. And that's all you need to do to graph an ellipse. There's what it looks like. There's the center, and there's the vertices right here. Here are the vertices, and the co-vertices are the other endpoints on the minor axis. Now this example, or these examples, want you to find the value of C, and this is really to just practice how do you find the value of C. Well, these values are related using the equation C squared equals A squared minus B squared. So what I'm going to do is I'm going to take A squared, which I know to be 81, and B squared, which I know to be 25, and I'm going to subtract them. And C squared equals 56. Well, I want the value of C. 56 is a non-perfect square. So how do I simplify this non-perfect square? The largest perfect square that goes into 56 is 4. 4 times 14 is 56. Therefore, the square root of 4 times the square root of 14 is the square root of 56. I can simplify the square root of 4 by 2, and 2 times the square root of 14 I can write like that. Which means C squared, if I take, oh, I'm sorry, the reason I did that is because I don't, when I'm undoing this square over here, I'm taking the square root of both sides. So I'm taking the square root of 56, which is 2 square roots of 14. And that's the length of C. Now, a lot of times, if you're ever asked to graph 2 square roots of 14, okay, well, if you plug that into your calculator, you get approximately 7.483, yada, yada, yada. So I know the foci are about 7 and a little more out to, let's see if that's at 9, 8, 7, it's like right there. And that's like 8, 7, it's like right there, right? So those are where my foci are, which you don't have to graph those on here. It's not asking you to, but if you're ever asked to, that's how you would. So let's move on to example number 2. We're still graphing ellipses. And here's an example where my center is not at 0, 0. My HK, the center, remember HK is found, and it's very similar to you know, the circles that we looked at, right? So your center, I'm going to be moving left 5 and up 2, right? So left 5 would be -5, and then up 2 would be +2. So my center is at -5, 2. Let's go ahead and graph that. So 1, 2, 3, 4, 5, and then up 2 is right there. There's my center, and now let's determine what if this ellipse is going to be vertical or horizontal. Now, again, I do want to point out right here that I am adding these two rational expressions right here. So make sure that is definitely something that you're looking for. Obviously, everything in today's notes will have you're adding these two, but that's what we're looking for. So I have these two denominators. One is 16 and one is 64. The larger number, which is right here, is obviously under the y, which means this is going to be a vertical ellipse, which looks like this. And I just like to write that down just to kind of remind me. So the A value is actually right here. This is A, which is A squared is 64, which means A is the square root of 64, which is 8. And in this case, let's go ahead and graph this on our coordinate plane. From the center, let's go 8 units up. That's one endpoint on my major axis. Then let's go down 8 units. 1, 2, 3, 4, 5, 6, 7, 8. 8 units down. That's the other endpoint on the major axis, which is vertical. And now let's look at the minor axis. The minor axis is found using with the values of b. And b squared I know to be 16, which means b is the square root of 16, which is 4. So the value of B is 4. So from the center, I'm going to go 1, 2, 3, 4 units out on each side. And those are the vertices and the co-vertices of this ellipse. And we can connect those endpoints. And now let's find the value of C. Again, these values are all related using the formula C squared equals A squared minus B squared. We've identified that the value of A, or A squared, I can see is 64, and the value of B squared is 16, which means C squared equals 64 minus 16, which is 48. If I want to find the value of C, I need to take the square root of both sides. So I need to take the square root of 48. When I simplify the square root of 48, I get the square root of 16 times the square root of 3. The square root of 16 is 4, which means this simplified is 4 root 3, or 4 square roots of 3. Which, again, if you use your calculator and you wanted to approximate it, that's approximately 6.928 blah, blah, blah. So 4 square roots of 3. Let's move on to number 3. So in this example, you first might think, hey, that doesn't look like an ellipse. When actually, let's change colors here, when actually this is set equal to 64. The equation will always be set equal to 1, which means I need to set this equation equal to 1. So one of the things I notice here is I'm still adding, which everything you're doing today, you will be adding. But if I were to set this equation equal to 1, I need to divide this by 64. What I do to one side, I have to do to the other. Each one of these terms gets divided by 64. So what happens is, when I simplify 4 over 64, I get 1 over 16, which means this simplifies to x minus 3 squared over 16 plus 16 over 64 simplifies to 1 over 4. So I can write that as y plus 1 squared over 4. Now I've got an equation that is set equal to 1. This is the equation for an ellipse. So let's first now figure out what's the center. The center of this ellipse is HK, which is what? 3, negative 1. Positive 3, negative 1. So let's go ahead and graph that. And now let's determine, is this going to be graphed vertically or horizontally? Like, what's that long side? What's the major axis? Is it vertical or horizontal? I can see that the larger number, the larger denominator, is under the x, which means this ellipse is horizontal. And I just like to write that down to just kind of refer to whenever I'm graphing. So now that long side will always be a, right? This is a squared, okay? So to find the value of a, I know that a squared is 16, which means the value of a is going to be the square root of 16, which is 4. Because that ellipse is horizontal, from the center, I'm going to go out 1, 2, 3, 4 units to the right, 1, 2, 3, 4 units to the left. Now let's find where our co-vertices are. Let me get a different color here. I know if that's a squared over there, this right here is b squared. So b squared is always the smaller number when you're looking at ellipses. It's always the smaller number. It's from the center to that co-vertex on your minor axis. If b squared is 4, then b is 2, which means from the center, I'm going to go up 2 units and down 2 units. And now I've graphed this ellipse, which looks like this. And this particular problem wants you to find the value of c. I know these values are related using this formula. C squared equals a squared minus b squared. which means c squared equals a squared is 16 and b squared is 4. 16 minus 4 is 12. So if I take the square root of 12, the biggest perfect square that goes in there is 4. So square root of 4 times the square root of 3. The square root of 4 is 2. So I can rewrite this as c equals 2 square roots of 3. And that's the value of c. So let's move on to writing equations of ellipses. We've moved on to the section of today's notes where we're going to be writing equations of ellipses. And there are some steps that you can refer to as we're writing through these equations, but keep in mind that every problem is going to give you a little bit different information, and you have to figure out what are we given and what do we need to know. But the first thing that I want you to do when you're writing an elliptical equation is choose the appropriate form of the equation. Which axis is longer? Is this horizontal or vertical? And then remember, if it's horizontal, a squared goes under whichever axis is bigger, right? So the bigger, if it's horizontal, the a squared is going to go under the x. So let's write that, a squared under x. And if it's vertical, a squared goes under y, right? That bigger number is going to go under the y value if that major axis is vertical. The next thing we're going to do is we're going to identify the values of a, b, and c using this equation. You really only need the values of a and b to write an equation, but sometimes you're not given the a or b value. You're given the c value, and you need to use this equation to find the missing value. Then we'll write the equation. So let's look at example number 4. It says to write the equation of the ellipse in standard form with center at 0, 0, an endpoint on the major axis at 5, 0, and the distance from the center to the focus equals 4. Okay, so let's talk about what we know. The first thing I know is that my center, HK, is 0, 0. Right? So we're not having any translations. We're not moving up, down, left, or right. We're just staying at the center, 0, 0. An endpoint on the major axis is 5, 0. Well, if I'm at 5, 0, if I'm at 0, 0 right here, and I'm moving 1, 2, 3, 4, 5, 0, I'm moving right 5 units. That major axis is going to be horizontal. So I'm going to write that down. Horizontal. I like to write this. Horizontal. That lets me know that a squared is going to go under the x. So I'm going to erase this over here. And now let's write some values for a, b, and c. Let's change colors here. So I know that the distance from the center to that vertex is a. And the distance is 5. I know that because I'm translating from 0, I'm not translating, but it's 5 units, right? If I'm going from 0, 0 to 5, 0, I've moved 5 units right, so that there's a distance of 5 there. So the a value is 5. Now what's my b value? Because that's the other value I need when I'm writing an equation. Well, I don't know that. I don't know the distance from the center to the co-vertex, but I do know the distance from the center to the focus, and that's our c value. C equals 4. So we're actually going to have to do a little algebra to figure out what our b value is. We know that these values are related using this equation. C squared equals a squared minus b squared. And in our previous examples, we didn't need the value of c when we were graphing, but we practiced it. So we're going to do that here. We know if c is 4, c squared is 16. If a is 5, a squared is 25 minus b squared. And now I'm going to do 16 minus 25, and I get negative 9. If negative b squared is negative 9, then b squared equals positive 9. And if b squared equals 9, I'm going to take the square root of both sides. B is going to be 3. There's our missing value. So now let's write this equation. I know, and here's what I like to do. I like to write my numerators first. So I know I've got x squared plus y squared, and I'm going to set it equal to 1, right? In standard form, the equation of an ellipse is set equal to 1. I know because it's horizontal, which I wrote right here, that my a value, which is right here, is going to go under the x term. So I'm going to write a squared under x squared, which is 25. B squared goes under y squared, which b is 3, which means b squared is 9. So here's my equation. X squared over 25 plus y squared over 9 equals 1. Let's go on to our next example. In our next example, moving down, number 5, it says to write the equation. Let's see here. I'm going to do that. Write the equation of the ellipse in standard form with major axis vertices at -3, 6 and 11, 6, where the distance from the center to the focus equals 2 root 10, or 2 square roots of 10. Okay, what are we given here? Well, first off, our major axis vertices. Let's think about this. If I have a point at -3, 6, that's going to be -3, 6, which is -3, 1, 2, 3, 4, 5, 6, and 11, 6, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right there, 11, 6. My major axis vertices are, or that tells me right there that my major axis is horizontal. So I'm going to write that down. That's horizontal. And I know that the center is going to be the midpoint of those two endpoints. So one of the things that I can do is I can use my midpoint formula to find the center of this line segment. So what I'm going to do is I'm going to find the midpoint. I'm going to add 11 plus -3, and I'm going to divide by 2. I'm going to add 6 plus 6, and then I'm going to divide by 2, and I get a midpoint of, let's see, that's going to be 8 over 2. This is going to be 12 over 2. We're just going to do a little bit at a time. And my midpoint is going to be 4, 6. Now, does that make sense? Okay, so 4, 6, 1, 2, 3, 4, and up 6. There is my center, 4, 6. And you can always check it, okay? So I know that the distance from 4 to 11, like the difference, is 7 units. And from 4 to -3 is also 7 units, right? The absolute value, the distance would be 7 units. So that makes sense that that is our midpoint. This is our HK, and I'll write it as such. That's our HK. HK equals. Okay, so now what else are we given? We know that we need values for A, B, and C. We know that our major axis is horizontal, which means our A value is that distance, right? It is that distance, which we just said was 7. So A is 7. We know that the distance from the center to the focus equals 2 square roots of 10. Well, that's our C value, 2 square roots of 10. We don't know our B value, so we're going to have to use our formula, C squared equals A squared minus B squared, to find our missing B value. So let's plug in these values. 2 root 10, well, 2 root 10 squared is looks like this. 2 root 10 squared. I'm going to square the 2, and I square the square root of 10. So I get 4 times 10, which is 40. So that's going to be 40. A squared is going to be 7 squared, which is 49, minus B squared. I'm going to subtract 49 from both sides, and I get -9 equals -B squared, and this looks like a lot like what we just did, which means B squared equals +9, which means B equals 3. I went pretty fast on that because we just did that in number 5. So the B value is 3. Now let's write our equation. I'm going to use this color right here. Okay, so our equation First, let's write our numerators, okay, because I'm going to use my center point to write those. I know that the numerator, using my HK, is going to be x minus 4 squared over something plus y minus 6 squared, and I'm going to set it equal to 1. So now I have these values of a, b, and c. I know my ellipse is horizontal, which means the a value goes under the x term. Well, if a is 7, a squared is 49. The b value is going to go under the y term. If b is 3, b squared is 9. And that's the equation for this ellipse. Let's move on to the next one. Finding the constant sum of an ellipse. So this is the last and final thing that we're going to do in today's lesson. And I know these are long notes. And some of you might not even be worried about constant sum. But I'm going to at least show you how to do it. Okay, so what is the constant sum? I talked about it earlier in the video. It's the sum of each focus to the same point on the ellipse is constant for all points on the ellipse. That's basically what constant sum is. So what we're going to do is use the distance formula, which I've shown above right here, to calculate the distance from each focus to the point on the ellipse. And if you need a little refresher over distance and you didn't watch the first video in this unit, I'll put a little card up there in the upper right corner of the screen that'll link you to how to use the distance formula. But we're going to be using it, and you may recall it from geometry. Then we'll add the two distances. So let's use, we just got one example on here. It says to find the constant sum of the ellipse with foci f sub 1 at negative 5, 0 and f sub 2 at 5, 0, and a point on the ellipse at 2, 4. So let's draw a little sketch so you can kind of picture what this is. We've got one focus at negative 5, 0. That is f1, f sub 1. And we've got our other focus at 5, 0. And that's labeled f sub 2. We have a point on the ellipse at 2, 4. So 2 up 1, 2, 3, 4. So here's our point on the ellipse. We're finding the constant sum. What we need to do is find the distance from this first focus, f sub 1, to that point on the ellipse. I'm going to call that d sub 1. So let's do that first over here, d sub 1. We're going to use that distance formula. The distance formula tells me I'm going to take the square root of, remember, and I'm going to go pretty quickly through this because I do have a whole video over reviewing the distance formula, but we're going to subtract the x values. So let's do 2 minus negative 5. We're going to square that. We're going to add it to the difference in the y values, which would be 4 minus 0. And then we'll square that. So d sub 1 equals, and this 2 minus negative 5 is the same thing as 2 plus 5, which is 7. 7 squared is 49. Plus 4 minus 0 is 4. And 4 squared is 16. So now we have 49 plus 16, which is 65. So I get the square root of 65 is the distance from that focus on the left to that point on the ellipse. Now let's find the distance from that point on the ellipse to this other focus, and we'll call that D2. And let's do that right over here. We're going to use the same formula, our distance formula, where we're going to take the square root of, we're going to subtract our x values, 2 minus 5, square that, add it to, now we're going to subtract our y values, which is 4 minus 0, and we're going to square that, which means 2 minus 5 is negative 3. Negative 3 squared is positive 9. So now I've got 9 plus 4 minus 0 is 4. 4 squared is 16. 9 plus 16 is 25. So I'm going to take the square root of 25, which is a perfect square, and I get 5. So the constant sum for this particular ellipse would be D1 plus D2, which is the square root of 65 plus 5. And I would write that 5 plus the square root of 65. Those aren't like terms, so I can't combine them. And that, it concludes your notes, your very long notes, over ellipses for conic sections. I hope these notes were helpful.